Well, let me know if you can't hear me or if I need to turn up my volume or anything. We are starting class a little later today, but we're basically going over Python overview, the concepts of object-oriented programming, as well as classes and class inheritance in Python. So since we're switching over from covering JavaScript material to Python material, I want to kick this off by just going over some of the key differences in syntax between the two languages. Um, I think one of the most obvious things is how finicky Python is about indentation. So indentation is essentially what Python uses as its code block delimiter, which is how the compiler will distinguish between what exists within a code block and what exists outside of that. In JavaScript, we know that we use curly braces, but in Python, we have to use proper indentation. So you need to be mindful of how far you indent, especially when you're looping or using statements or creating functions. Some of the other differences include commenting is just using slightly different syntax. So we use hashes in Python with triple ticks for a multi-line comment. And we use forward slashes with stars in JavaScript for the multi-line comments. Variables are dynamically typed in both, but JavaScript is a little more particular about you defining the variable first. You have to utilize keywords like var or const or let, which you do not have to do in Python. Your variables in Python are dynamically typed at runtime. So you can just create a variable, like in this example here, var underscore name, and you can set it to your value right away. Strings in both utilize both single and double quotes. Specifically in JavaScript for string interpolation, you want to use backticks with a $sign and curly brackets. In Python, you have a choice between the F statement, or I'm actually blanking on the syntax for single interpolation for Python, but it is a little different from JavaScript. Loops, just like in JavaScript, we are able to loop. The syntax in Python isn't as, let's say, complicated as it is in JavaScript, because JavaScript's for syntax requires 3 parameters, whereas in Python, you have something that very much resembles the JavaScript for in loop. So you're iterating through an iterable object in Python by just passing in what you want to associate each index item with. So in this case, we're naming each value at each index of this iterable as item, and you don't have to specify like the length to which you want to stop or how to increment or decrement your index. Arrays and lists are pretty much the same. Same with dictionaries and objects. They just have slightly different names. So aside from the names being different, they operate exactly the same. When it comes to creating methods, functions, and classes, declaration is a little different as well. In JavaScript, we use the function keyword, whereas in Python, the keyword is def or define. If, else, else if is a little different as well, because else if is truncated to elif. Classes in Python, we don't use curly brackets like we do in JavaScript. We just use parentheses for, well, we use the parentheses for parameters, but we use indentation as the code block delimiter. When it comes to our method definitions, it's very similar to the functions. I don't know if I've said this yet, but the difference between functions and methods is very minimal. I actually want to ask, Can anyone tell me what the difference between a function and a method is? It's a pretty simple difference.
Is a method without method is something that has to do with class.
Exactly. Methods are essentially functions that exist within a class. Yes. So very slight difference, but it is key to understand if you are trying to access that functionality outside or from within a class. You just have to be mindful of that. Constructors are very different between Python and JavaScript. We use this underscore underscore init underscore underscore format in Python, whereas JavaScript is a little more, if not a lot more, user-friendly and easy to read and understand. We use the keyword constructor. Inheritance is a little simpler, I think, in Python. JavaScript's a little more verbose, but it maybe is a little more clear what's happening here because the syntax for inheritance in Python looks very similar to a regular function taking in a parameter, whereas JavaScript makes it clear that by using the extends keyword, we are using inheritance. All right, last key differences between the two in terms of syntax. When you're importing modules, you need to pass in the path for JavaScript. Exception handling, similar format, just slightly different keywords. We use catch in JavaScript and except in Python. Closure is the same, and scope is pretty much the same with JavaScript having additional block level scope. All right, higher order functions. We talked about this in JavaScript just yesterday, so we don't really have to go too heavily in detail about this, but as a recap, somebody tell me what a higher order function is. Most of the folks are inside room one, so Troy, what about you? What is a higher order function?
um, a higher order function, I thought we were saying either is a recipient coming from another function or is going to another function.
Exactly, exactly. When that kind of behavior is occurring, both functions are called and considered higher order functions. So in JavaScript, essentially a function is higher order when, unlike a first order function, which works with first class data objects like strings, booleans, arrays, etc., higher order functions have an additional layer of complexity and abstraction because they're now manipulating other functions which are not simple data types. So that is why we call them higher order functions. Let's actually go back one slide. Let's look at the syntax real quick. We see in JavaScript, we basically can, there are many ways to do it in JavaScript, right? Because yesterday we covered various other types of function syntax. So we have our regular function notation using the function keyword, and then we have functions that could be written using lambda expressions, which are just parameters on the left side, an arrow in the middle, and the expression on the right side. And then we also have something called queried functions, where a function, it's a higher order function that essentially consists of functions that each take in a single parameter. And so you can either define a new function out of another higher order function, or you could just call that higher order function and pass in both parameters. In Python, syntax is a little different. So behavior concept is essentially the same, higher order functions in Python are both functions that accept and send out other functions. So functions can be passed as arguments and returned from other functions and assigned to variables. Just like in JavaScript, which has for each map, filter, and reduce as built-in functions, we have map, filter, and reduce in Python, but we do not have for each. For each does not exist in Python. So instead of for each, we can just use a for loop, which syntactically is a lot simpler in Python, which kind of eliminates the need for a for each. Okay, higher order functions in Python. We also have a list, which is a constructor that will take an iterable object like a string or a tuple, and then it returns an array. So very similar to map. We also have map, which has the additional behavior of being able to take in multiple parameters. So here we see in this bottom example for square map, we take the original calculate square method, and then we also take in numbers so that we can apply or call calculate square with numbers passed in as the parameter. Let's see. A map object in Python may not appear just like you would expect, so you could loop through it or convert it to a list. We also have filter, which behaves just like it does in JavaScript. It allows us to take an iterable object, and we also pass in a function. In this case, we're passing in this check if even function. So with numbers as our second argument, check if even will run, taking that number's iterable, that array, that list, and it will then produce results based on the index of this iterable. So either returns true or returns false. And if it's true, then it will spit out the value at the index for which it is true. Okay, now what are classes? What are classes? Let's have somebody try to explain it. So who wants to take a stab at it?
I already have it on the screen, Julie. It's a template for creating objects.
I do have it on the screen. Yeah, so that is definitely one way of describing it. I was wondering if anybody would want to like try to take a stab at a more creative definition, but yes, essentially they're templates, they're blueprints. They're ways for us to reutilize variables and methods, and we do this through something called instantiation, right? So if you think of a class as a template or a blueprint, you just create it once, and then you can use that to produce multiple copies. Let's see. So we use the word class to define classes. The attributes themselves are also defined within the class, and instance objects will then contain these very attributes from which they are instantiated. And we also can access these instance attributes using dot notation. So in this example here, we have a new instance of an object, which is just called instance name. And we could then say instance name dot class attribute string or something like that. And it will give us the value that was passed in from the original class. When we talk a little more about instantiation, we'll also see that we can modify these values. So while it may While an instance of a class may inherit the default values of its parent class of the blueprint that it's instantiated from, we could also modify these values because they become unique to the instance. But why do we want to instantiate in the first place? If we look at this example, we see that we have a book, a new book created from a book class. And if we were to print out the title or the author, it would return the title and author that was defined in the original book. But let's say we have a lot of these new books. If we try to update one or read from one, it will be the same for all of them because they're all inherited from the parent. And if we want to try to update these manually, we would have to update each new instance individually, which will be very cumbersome and tedious. So we use instantiation instead to allow us to much more efficiently and quickly update these values. In this instance, our book class has self, title, and author as arguments. We utilize this underscore init method, which basically takes in an object called self. Self is a very unique Python keyword. And from here, you can write the rest of this class as you see fit, like adding whatever arguments or methods you want. But what's great about this init method is it allows us to say that these are parameters that can be updated for each instance. So every book will have its own title and will have its own author. When we instantiate that book class, we could also immediately pass in these arguments. So here we're saying we want the title to be Catcher in the Rye, and we want the author to be J.D. Salinger. Pay attention to the position of these arguments in these parentheses. Here we see that the title is the first thing. Here we see author is the second thing. But in the original book class, self is actually the first argument. Title and author are second and third. When I said that the self keyword is unique, it has some very interesting behavior, such as being ignored, essentially, when you instantiate an instance of a class. You don't have to redefine self or explicitly say, I want to pass in self. You only have to specify it when you're creating the class itself. I know it's a little confusing, but that's just how Python is written. This way, whenever we make a new book, unlike in the previous example where we're just simply instantiating the book without passing in parameters, we can off the bat tell it what we want to update these values to. All right, the last thing we're going to cover is something that you're actually going to be covering a little more in depth on Saturday. So maybe we'll just try to breeze through this a bit. But basically, inheritance is a mechanism where properties are passed down from a parent class to a child class. So similar to what we're seeing here, where the parameters, the values are being passed down from the blueprint to the instance, the same occurs when we're inheriting from a parent class to a child class. Now, maybe I just want to make sure like this doesn't become confusing, but we're talking about two very different things, right? The first thing that we talked about is classes and class instantiation. We're not even thinking about parents and children at this point. So now I actually kind of already regret talking about inheritance because it might confuse things, but I'm just going to breeze through it real quick. What inheritance is what happens when you're creating a subset of another class. child class is essentially a copy of parent class. And that's why when we call a class child class, when we're defining this class, we are able to pass in parent class as an argument saying that we want this to be a subclass of parent class. So what makes that so different from class and inheritance? Well, the child class itself is also a blueprint. So now we could instantiate the child class the way that we could instantiate the parent. And again, I still regret going into this so soon. There not only is there single inheritance, but there's multiple inheritance, there's multi-level inheritance. So there are many different ways to replicate a lot of the code and attributes and functionality that you create from parent to a new method. So hierarchical inheritance is essentially just a combination of all of the above in some kind of fashion. And then the last thing that maybe we want to talk about is something called I'm blanking on what it's called, but basically there's also composition that refers to a very specific principle that I'm blanking on, but composition is slightly different from inheritance. You could think of inheritance as an is a relationship. So a software engineer is an employee. But if you take a compositional approach to your functions, it's more of a has a relationship. So we have an employee class that has a title class, a department class, a pay rate class. How it calls the methods and attributes from these other relationships is the key difference between these two. When we're inheriting, we're taking from the parent. When we're composing, we're essentially nesting. Like the title class exists within the employee. The software engineer class does not exist within the employee, and the employee does not exist within the software engineer class. They're two different blueprints. Whereas title is a blueprint within a blueprint. It's a blueprint within employee. Department is another blueprint within employee. All right. Does all of that more or less make sense?
Well, I thought I was following you until you said software engineer does not have employee. Like this slide, everything was like a top down on the previous slides. So this one with the arrows going bottom up just had me a little visually confused. But if software engineer is if employee is taking inheritance from software engineer, does that mean software engineers' attributes and methods are part of employees' class, same attributes, same methods, but in addition, employee might have more attributes and methods? Or
Exactly. Yes, that's what happens with a child class. And my apologies, these arrows really should be going in reverse. At least for this side, yeah, so this slide is definitely confusing. That is on me. Technically, if you were writing this out, you would want the employee to be the parent class and the software engineer to be the child class.
okay. I did get lost at composition though, just in terms of, thinking about attributes and methods, what's being shared between the title class and an employee class along lines of attributes and methods.
Sure. Yeah, let me see if I have let me see if I updated the README with a good example, because yeah. Oh, here's another example. Is it sharing or is it just doing the, okay. So think of it as like a different way of writing your components, right? So it's like totally unrelated to inheritance. It's like a completely different thing. So in a way, it's like we're comparing apples and oranges, but they are because they are different approaches to what is essentially like the same end result, which is replicating, making code reusable, it's good to be able to compare the two. So that's what it was called, the composite reuse principle. That's what I was trying to think of. But right, as different approaches, we can think about let's use a different example. Let's use a car example. So if we were writing in the style of, dang, the other part's not in here. Or it is, but it's just not formatted properly. If we were writing in the style of inheritance, we might say we have a vehicle class. And an example of that might be a car, like a car is a vehicle. A vehicle is not necessarily a car because a boat is also a vehicle, right? So this is like a parent-child kind of relationship. The child, in this case, the car, is inheriting properties from the vehicle. Like, let's say all vehicles need fuel, right? So in that kind of model, it makes sense to be able to pass down a shared property from one parent to multiple children. Now, let's say we were focused on different things, right? Like maybe we're not so concerned about, well, actually, let's not even think about our concern. In this example, we're thinking about a different kind of relationship. Instead of thinking hierarchically, like, what is a car? Oh, it's a vehicle. What are examples of vehicles? It's a car. We're thinking about this now in terms of like the behaviors or the actions or the properties that a car composes of, right? So what does a car need to be able to do? It needs to be able to move around, so it needs wheels. It needs to be able to run on some kind of fuel, so it needs an engine. And these are all different classes that can be shared between other classes. So a boat can also utilize an engine. It may not utilize wheels, but how we call them is the key difference. So here, inside of our car class, when we're writing our init, we're creating an engine and a wheels property within the car. And when we create this attribute, this property, so a car will have an engine and a car will have a wheel or wheels, we call these other classes. So we're instantiating an engine within the car. We're instantiating wheels within the car. That kind of relationship doesn't really exist with parents and classes, because I guess maybe you could say an engine is a child of a car. Maybe you could say wheels are a child of a car, but that would dynamically change how you write out the methods, right? By doing it this way with a composite reuse formula, like let's say engine, let's just say engine has or let's use wheels as an example. Wheels has a method called spin, right? Because wheels exists inside of car, we could just say self.wheels.spins, which is the name of the method inside wheels. That wouldn't be the case in a parent-child relationship. If this was a parent-child relationship, the syntax would be slightly different. So yeah, does that help?
On a super init, is the super init up above on the child parent inheritance? Is the super init giving the child everything that the vehicle had? Is that what super?
Yep, yep. So I think there might be a better example of the super init somewhere else. But yes, that's essentially what it's doing.
Okay. And so when you're doing a composite, I'm really trying to understand the difference between just giving everything to the class or defining it as this attribute that references this other class. And what's the benefit in doing that?
Let's see.
Methods from superclasses should be those classes that contain these methods. Okay. Maybe if I read slower.
So basically, if you're trying to establish a relationship between objects, but there are different kinds of relationship, right? So,
Mhm.
so that object imaging can become an attribute of another object.
Exactly, yes.
Okay.
As for the specific pros and cons, let's see. They both share a lot of similarities, right? Because in terms of like the why, as for why we're doing this, is because it allows for things like code reusability, right? So we're reusing code from the base class when we're doing class inheritance. We're still reusing code when we're using composition, just calling it slightly different. Functionality is shared among the subclasses, whereas components can be reused independently. I don't think that's very clear, but let me take a stab at this. So the shared functionality among subclasses. It is still very similar, right? Because if we have multiple subclasses like a car and a boat, they would take in parameters that are created in the vehicle and they would be shared amongst all of the subclasses. Likewise, if we had a vehicle, or sorry, if we had a boat that also had an engine, it would also be able to reuse that functionality. I don't think the wording is so great on this. Let's talk about some of these other comparisons then. So one enables polymorphic behavior. Polymorphism may require more explicit implementation. Let's not even worry about that. I think this one's key right here. So this is a clear reference to like an is a relationship. This is a clear separation of concerns. So I do think conceptually, that's one of the practical differences, essentially like how you're communicating to other people on your team or users if you're making like some kind of public API, how this class is supposed to work. If we go back to are is a versus has a, like that's I think really key, like just like the conversion of these relationships to English, right? Because at the end of the day, a lot of the end result is similar. We're reusing code and we're able to have shared properties. But in terms of like what the end result is for an organization or for users, in a way it is just kind of semantics, right? Ease maybe composition can get very cluttered at like a kind of horizontal level, right? Like if we have a lot of different behaviors or components that class has to compose of, that can be very difficult to navigate and track in a code base as you're trying to find the right functionality to change. With inheritance, you might find more of that behavior grouped into a parent, and there's more risk of vertical complexity where you have a lot of children of children of children. So they could, both procedures, both processes, both approaches can become complex, far too complex for practicality's sake, which is what's often called as monolithic code or tech debt, but it just happens in different ways, right? Because these are just different trees, basically, different ways of essentially achieving the same thing in the end. Is that making it a little more clear, or is that just confusing it even more? I'm sorry.
Helping here. Slowly.
Right on. I say one of the best things to do is to take a stab at both approaches and just see for yourself. And that really is the best way. I think by doing it that way, you'll be able to formulate these questions over and over in your mind and then see firsthand what differences stick out to you, right? So I think I can go on and on and on trying to explain this, but really seeing and experiencing firsthand is what's going to make it clear. I think that's the end of what we've got. Let's see what we have in terms of challenges. Oh, that's day 4. Okay, that's why I think it confused me. All right, we have Roman numerals, credit check, anagrams, and reading errors. Make sure all these links work. I think you all have already done Roman numerals once or twice, but now we're just going to be doing these in Python. So cool. Let me cut the recording, and breakout rooms are open, and we will reconvene.